Good afternoon, class. This is Chih-Heng Lu from National Tsinghua University, and today we invite Dr. Yunung Lin. He is easygoing, so you can call her Nina. The topic she will deliver is the SAR image processing using Snap. She showed up before in the class. So you all should meet her already, and she currently serves as assistant research fellow in Institute of Earth Science, Academia Sinica, Taiwan. And her main research interests include natural hazard monitoring with InSAR and change detection using InSAR, but not limited to that. Okay, so stage is yours, Nina.
Okay, thank you, Chang-Heng. Hi, everyone. I'm Nina. So today is my honor and my pleasure to talk about SNAP. Okay, so here, some of you may be wondering, why do we bother? Okay, some people may wonder, oh, there are many other fancier tools than SNAP. Then why do we bother to use SNAP? Okay, so of course, one of fundamental reason that we are trying SNAP today is because this is actually one of the few open source the software that process SAR data that is cross-platform. Okay, because according to the survey, most of you are actually using Windows. Only very few people are running a Linux system. So in this case, you are probably left with a very small number of choices. Okay, Snap will be your probably your only choice if you want to go with open source. Okay. However, having that said, it doesn't mean that Snap is is not a good tool. Actually, to be honest, it is a more powerful tool than we probably had ever imagined. Okay, so some introduction about Snap. So it is a Java-based software, and actually it is open sourced. If you know how to use GitHub, okay, you can go to GitHub and Google Snap, and you will be able to visit all the source code of Snap. Okay, you will be able to, by reading the code, you will be able to understand what each individual step is doing. Of course, you need to be able to speak Java, okay? And again, as I mentioned, it is cross-platform. So it is very, very suitable for teaching, especially for most of the newbies who know very little or nothing about SAR processing. Okay, this will be your best tool. And it also offers a embedded graphic user interface, GUI. So you won't be you do not need to bother like using all the other plotting softwares to plot the results. Okay, so this is, if you ever use other softwares, then you will know what I mean. Okay, so there are actually, so Snap, why I'm saying Snap is powerful is because it supports different modes, okay, for different levels of users. So if you are basically a beginner, knows nothing about satellite image processing, okay? So you actually support this so-called click button mode, okay? You just need to know how to click the buttons, and then you will be able to produce the results. However, if you are an advanced user, okay, you know how to speak Python or any other languages, okay? It actually support so-called large-scale computation, okay? By calling directly this thing called the graphic processing tool, or in acronym GPT, okay? So actually that is exactly what we're doing in IES, in Academia Sinica. We are not using the graphic interface. We're directly calling GPT and doing parallel processing directly, okay? So that's why I'm saying it is quite powerful, because none of the other SAR processing softwares allow you to do this, okay? Allowing these different levels of users, okay? And finally, one of the property that I value Snap the most is that it actually supports many commercial SAR satellite data, okay? So for example, when at the time when InSAR, okay, so it is the Finland SAR satellite, okay, and it is a commercial satellite. So when it is first launched and issued the test data, okay, SNAP already has the capability of reading in the InSAR data, okay, while all the other softwares are lagging behind. Of course, you can argue that it probably support more of the European satellite because obviously SNAP is a product of ESA, right? So, but still, that still allow you to use many European satellite products, okay? So based on all these perspectives, I suggest that even though you may be very familiar with other processing softwares already, but it doesn't hurt to learn SNAP, okay? And of course, since there are pros, there will be cons, right? So these are the cons, and you may find some of them a bit annoying, okay? So first of all, because it is based on Java, okay? So it is not really computationally efficient, okay? So that's why later in the demonstration, you will be required to only select a very small area. Otherwise, it will easily overwhelm your PC, okay? Unless you're not using PC. If you're using a Linux workstation, then you're probably fine, okay? But you need to remember it is not super efficient compared to other processing softwares that are based on C or Fortran, okay? Okay, and then also because it is based on Java, and I think in the scientific community, we don't speak Java that much, okay? We speak more C, Fortran, Python, MATLAB, okay? So to most of us, it is not that straightforward if you want to modify the code. Also, once you modify, you need to know how to compile, I guess, okay? I don't speak Java, so I really don't know how to do that, okay? So, and one thing that's a bit annoying is that still till now, it doesn't support the Ya-Lun S ScanSAR mode, okay? However, I know most of you are based in Southeast Asia, so you may find that Ya-Lun S ScanSAR are very critical to your work, okay? But in this case, unfortunately, SNAP doesn't support the ScanSAR mode. It only supports the stream map mode. And I think some of you was asking about the tropospheric correction, and unfortunately, it doesn't support any tropospheric correction or ionospheric correction either, okay? When we're talking about SAR interferometry, okay? If you want to do that, you need to use other softwares, okay? So, you can go back to visit the talk last week by Dr. Lu. He mentioned about many other softwares, okay? Some of them support the correction. Finally, it does not include any advanced fancy InSAR time series analysis, okay? So in this regard, some of you may already feel disappointed, okay? So from my work, I don't really rely on the SNAP to produce that much of my interferograms. However, if you know how to, or if you have a large enough PC, okay, such as a computer of many processors, okay, you can still produce some inputs that are used in other processing softwares, such as STEMPS, which is for persistent scatter InSAR processing, okay? However, SNAP itself does not support any of these time series analysis. Okay, so without further ado, then we will directly move on to SNAP. And as I mentioned, because SNAP supports many modes, so what I'm trying to teach is that I'm not going to go through this so-called click button modes, okay? Because people easily forget what are the sequence, okay, of the button clicking. However, if we do it by going to some kind of a linkage with a graphic processing tool, then you can save your processing flows, okay? And later on, you can easily apply the flow to your other projects, okay? And they also give you some records about what parameters you were using in the data processing, okay? So the reason why I'm teaching all this information is because some of you may still remember that at the end of this workshop, you are encouraged to present a small project, okay? Some of you may be panicked because you may be newbie and you know very little about SAR processing. But if now you have already had this guide with you, okay, I believe most of you have obtained the guide. So by going through the demo today, if you couldn't catch up, you can still follow the steps in the slide, and you will be able to produce something on your own. And I think that will be sufficient for the final presentation. If you are willing, I highly encourage you to do so. You don't really need to present something fancy, but if you are willing to present a small project that actually help you know deeper about the property of the data that you're using, okay? All right, so before starting, I want to remind you again that maybe already pay attention to this, but just another reminder that later we have this data structure. So if you didn't follow the data structure, then that's too bad because you may get lost during the demonstration, okay? So if you did, then congratulations, okay? So the data is for the source data. Project is where we're going to save all the intermediate products, okay, from SNAP. And finally, the XML is where we are saving the so-called graphic file, okay, which is the file that's also used by GPT. Okay. All right, so let's go to the PowerPoint about the, okay, I'm not going to go through the PowerPoint today, okay? So I'm going to directly demo, but first of all, there is a section called the data access through SNAP, okay? So this is just another way on top of the way, the instruction I offered last week about downloading and searching for data in ASF Vertex, okay? So you can actually also access the data through SNAP. Through SNAP. So here are some introductions. I'm not going through them, but still you will need to have a ASF account and password ready, okay? But anyway, I don't usually use this function, but this is only for your reference, okay? This is a way to do that. All right, okay, so let's start from the so-called backscattering coefficient, okay? So what is this relevant for, okay? The backscattering, or sigma naught, is, if you still remember from Dr. Alan Tsai's talk, okay, which is maybe the second and third week of this workshop, okay? He talked about so-called normalized radar cross-section, okay? So one of the so-called normalized radar cross-section is so-called sigma naught, okay? So this coefficient is actually constantly used in the field called change detection, okay? So actually, many people are not familiar with the change detection, okay? Because most people, when talking about SAR, they only know, oh, I know InSAR, I know it can be used to detect the earthquake, or to detect the land subsidence, or detect the ground movement associated with the landslide creeping, and so on. But actually, SAR has a wider application than that, okay? Are we going to get the slides after class? I think you already obtained the slides, okay? So TSU has already presented out the slides, okay? So if you're not, then you need to contact the TSU secretary. So so the major usage, okay, for this is to detect landslide. Okay, when we say detect, we don't mean to detect the deformation of the landslide, but it's more like, for example, if you have a earthquake happen, like the example I'm showing here, the 2018 Hokkaido earthquake, okay? And when it happened, it's very rainy with a lot of clouds, and it occurred at night, okay? You can imagine there's no way for you to obtain any optical image, okay? So in that case, radar image, as you know, is microwave. The radar microwave can actually penetrate the clouds. And it doesn't need to be during the daytime, right? The acquisition can be at night. So it will still allow you to detect the landslides on the ground, okay? And the same with floods, okay? If the flood happened at night, okay, which is I'm going to talk about in another 2 weeks, then that still allows you to detect the floods, all right? So that's why so-called the radar-based change detection has become more and more popular during the past decade. Okay, so it is actually something pretty, I would say, pretty recent. Okay, before after people finally turned their eyes from radar interferometry, but into more other applications related to hazards. Okay, all right. So let's move on to SNAP. Okay. Let me also check the slides. Okay. I want to make sure that I more or less follow the steps. Okay, so you're now seeing the interface of SNAP, and please also open the SNAP on your side. All right. So there are many tools up here, but basically the only tool that we're going to use is this one, okay, which is called the Graph Builder. Okay. So again, as I mentioned, this Graph Builder at the end will be saved as a XML file, okay, and that can be used for mass production. Okay, so now we enter the Graph Builder. Okay, so the first thing you need to remember is that, so above is the window for you to view the different building blocks, okay, and below is the parameter setting for each building block. But you need to remember, it's actually, even though you may like to add some processes in the middle, but eventually somehow it will more or less follow the flows, the sequence, the way that you're adding in. Okay, so for example, if I add something random here, okay, such as that, and below you will see it will do read, write, and cross correlation, okay, which is the wrong order, right? So in that case, I would delete it, okay, and I would also like to delete the write, okay, so that we add the blocks in the correct order, okay? All right, so now let's start by the most basic flow, which is to create a graph by yourself, okay? So you need to learn how to do that before you use other people's example, okay? So here you have this read, and then now we're going to start from the Hokkaido example, right? So let's go to the, okay, the SAR, okay, I think you call it SAR course, okay, although I have a SAR mini course here, but it's the same thing, okay. Go to data, go to Taiwan, go to Japan, okay, and then now I assume you have two GRD files, correct? Okay, so this GRD, I don't remember if this is mentioned, but I think so, which is that GRD, the difference between GRD and the SLC, the other format, is that the GRD file no longer contains the phase information. It only retains the amplitude, or you can also consider the intensity information of the SAR image, okay? So now let's open the pre-event GRD, which is the one on September 9th, 2018, okay? So we do select, all right. Okay, so and for the format, you can keep it because I think it's going to detect the right format anyway. Okay, and we know the GRD form, the one single frame, okay? So this data that we download from ASF is actually a complete frame, okay, which is cover, the weight is something like 300 kilometers maybe. So it's very large. We don't really want to spend time processing such a large image. So we want to do a subset, okay? So what you do is you do add, okay? Right click and add, and go to radar, and go to, go to raster, and go to subset, right here, okay? And then in the subset, you need to, and then now I'm going to link these two blocks. So you see when I move my cursor close to the read block, you see a red arrow, right? And you draw it to point to the subset directory, the subset block, okay? So that you form this red arrow. All right, so now in the subset folder, you start to see that it has 4 channels, okay? Amplitude, VH polarization, okay? Amplitude, intensity, VV polarization, okay? And I said you actually can select only one, or you don't select any, then by default it's going to subset on all the channels, okay? All 4 channels. Okay, now let's go to the actual subset. So to do the actual subset, you need to go to the geographic coordinate. Okay, so let me pull this up. All right. So in this view, okay, it's a bit difficult to see where we are, okay, because I think we're around, the target area is Japan, so it's around there. So so as I mentioned, you need to have a mouse, okay? If you don't have a mouse, then I cannot help you now, okay? Use the middle wheel to zoom in, okay? So zoom in, use the middle wheel, and use your right button to move, okay? So I'm using my right button to move. And keep zooming in, and right button to move. Okay, zooming in to move. Okay, I hope you catch up. Okay, again, let me remind you, middle wheel is zoom in, zoom out, and the right button is to move. Now we are in Hokkaido area, and the red frame is actually the footprint of this GRD, right? Okay, so now I zoom in a little bit more. Okay, so because I had to study this area before, so I can tell you it is not the whole frame that you will see landslides. Okay, landslide only occurred in a particular area, which is around here. Okay, so now use your left button to click and drag and release. Okay, are you with me? Okay, let me check the window to see. Okay, so if you have any question, you need to raise your hands or you need to type, okay? Otherwise, we will just move on. Okay, so I assume it is pretty okay for most of you. Then we have already draw a yellow LOI, and if you hit the update, sorry. I think it's already. Okay, let's just leave it here. All right. So now we already tell Snap that we want to only work on this small yellow box, right? And then let's move on to add the next block. Okay. So you automatically adding the coordinate, the bounding box coordinates of the AOI we just drawn. Now the next one is to apply orbit file. Okay. So the good thing, just to say something about the orbit file. So in Snap, it is quite smart that it downloads the orbit file automatically by itself. Okay. So in some other SAR processing softwares, it also does that. However, it is not the case for all the SAR processing softwares. Okay? So for some of the softwares, you actually need to pre-download the orbit files. Okay, and that can be a bit problem-taking. Can be quite problematic. All right. So so that's one thing again. One thing good about Snap. So let's go to radar. And the last one, apply orbit file. Okay, click. And you draw the arrow to the apply orbit file. Okay. So now let's look at the options in the orbit state vectors. Okay. So actually we don't change anything, but we just want to look at the options. Okay. So because we're working on the sentinel orbits, there are 2 different types. One is the sentinel precise. The other is the sentinel restituted. Okay. So the difference between these 2 is that there is a 3-week latency for the for InSAR. to release the sentinel precise orbit. Okay, so for example, if you are trying to process an image acquired today, there's no way that you can obtain the sentinel precise orbit. You can only obtain the sentinel restituted orbit. Okay, so that's why I'm saying it can be a bit problematic if you are working using a software that asks you to download the orbit by yourself. Okay, then you need to determine, oh, am I supposed to use the precise or the restituted orbit? Okay, but here in SNAP is actually quite smart. I believe that if you can always keep the default option of precise, and then if it couldn't find it, it's probably going to download the restituted orbit. Okay. All right, and then click do not fail if new orbit file is not found. Okay, so that's what I just mentioned. So now we reading the data, clip the image by using a smaller ALI, and we apply the orbit file. So the next one is that we want to convert the data, which is the amplitude and intensity, into sigma naught, okay, which is by normalizing the rate, normalizing the intensity and the intensity into a particular area, okay, so that you can do a proper comparison, okay, between images. So now let's go to add radar, radiometric, and calibration. Okay, radar, radiometric, calibration. Okay, add, and again we draw the link. So the next one. So it's asking, oh, do you want to do VV mode or do you want to do VH mode? Okay, so you can just leave it blank so that it's going to work on the two modes. And to say a few things about the different modes, okay, Dr. Ya-Lun Tsai, he actually mentioned about different polarizations a bit, okay? So V and H, the first V and the second H and V stands for the transmitting and the receiving polarization, right? And the reason why there are different polarizations is because they have different sensitivity to different link cover types. Okay, so for example, if you want to detect the flood, you need to figure out which mode, which polarization is better for flood. And if you're trying to detect landslide, you also need to figure out which one is better. Okay, so it's actually something that can be, can be formed into a mini project. Okay, if you are interested in presenting a mini project, this will be a good target. Okay, by comparing the landslide detection results or flood detection results by using polarizations, it will allow you to, it will give you this understanding about, which one is better. Okay, and to me that would be a really nice a really nice target to present at the end. Okay, so now let's just click on the sigma naught band. Okay, sigma, gamma, and beta naught are just different normalizations. Okay, so here, this is the end of the first section. So before we hit the run, you can choose to save. Okay, although in the slide I didn't ask you to save. Okay, you can choose to save, but it's not required at this moment because we're going to continue on in this current builder. So I'm going to run for now. Okay. If you have any question, you can ask now. All right, I'm done. And you are seeing nothing on the screen. That's totally normal, okay? Don't panic because we didn't give a write, which is the output option, okay? So you're not going to see anything on the screen. Okay, but the reason why I click a run for now is just to ensure that it goes through the first 4 steps, okay, without any issue. Okay, so if you are also opening the slide and moving on to session 3, okay, we're going to do thermal noise removal, terrain correction, and write. Okay, moving on. So in the next step, we're not just doing the calibration, okay? So the calibration is more like to calibrate different, let me see, is to, I forgot which one. Yeah, I did it before, but one of it is to calibrate the different effects at different part of the burst. Okay, so actually in different part of burst, from the part closer to the satellite to the part farther to the satellite, the energy, you can imagine, the energy is not evenly, is not distributed the same way. Okay, simply because the area closer to the satellite, okay, your energy is distributed onto a smaller ground area, whereas when the ray is going farther away from the satellite, okay, the same amount of energy is actually distributed in a larger area. Okay, so the normalized radar cross section is more or less to correct for this issue. Okay, and then the thermal noise calibration. Okay, so let's do it. Radiometric, okay, thermal noise removal. Okay, radar radiometric thermal noise removal. Okay, so this correction is to further correct for the, because on the satellite system, you actually have different temperatures, okay? And temperature is causing another type of noise. So if you really want to use the intensity information to do any ground, to do any change detection, you better remove the effects of the temperature changes as well, okay? So that's why we not only normalize the energy, okay, into sigma naught, we also try to correct for the thermal noise. So again, you don't need to change anything, just work on both bands, okay, and remove the thermal noise. And that's it. You can also choose to output the noise later if you're curious, okay? So finally, before writing out, the final step is radar geometric terrain correction and the terrain correction. Okay. So there is another one called the SAR terrain correction. Okay. Actually, this one is more advanced, and from my opinion, it's more accurate, but it's going to take a long time. Okay. So I would suggest let's do it now. If you're curious, you can try this one later as well. Okay. Terrain correction. So what does it do in the terrain correction? Let's have a look. Okay, so it input the bands, and the good thing again now is that it's going to download the DEM automatically for you. Okay, that's actually a very good thing. Okay, because in many SAR processing softwares, you need to prepare the DEM in advance. Okay, and that's a bit troublesome. Okay, so now please choose the SRTM 1 second HGT. Okay, again, automatic download. Okay, and here it's asking you, what is the ground resolution that you are going to choose? Okay, so now the default ground resolution, or maybe we shouldn't say ground resolution, okay? Because when we say resolution, we infer to the amount of information, okay, within a ground unit, okay? However, if you go out and ask the SAR community, and ask them, oh, what should be the ground resolution of Sentinel-1? And if you say 10 meters, then people will probably be laughing at you, okay? And the reason is because here we're talking about pixel spacing, okay? And in some cases, people use another term called the posting, Okay, it's like the the post on the ground. Okay, so pixel spacing or pixel posting, which is more like how we like to present the data at the ground. Okay, we choose to present every 10 meters. But it is not the same as saying the original data contains a 10-meter resolution information. Okay, so actually, in the origin, people like to say that the more like close to the actual situation is the resolution is closer to 15 meters, and in some cases, people may even say 20 meters. That's because it's depending on, as I mentioned, depending on whether if you're closer to the satellite, something we call the near range, or if you are farther from the satellite in the far range. Okay, if you're the area you're interested in is farther, then your resolution is probably closer to 20 meters. Okay, so again, don't mistaken. I have some echoes.
Nina.
Yes.
Sorry to interrupt you. I had a question from Louis.
Oh, okay, sorry. Can we select SLC product to do this processing? Is there any advantage if disadvantage in using SLC over the GRD for this purpose? Okay, so good question. Actually, there are people proposing to do the SLC to GRD conversion in Snap. Actually, you can do that as well. And then if you do so, I think you won't be able to retain the 10-meter spatial spacing. Okay. Actually, if you check I actually did this conversion before. Okay, and then I think I resampled the image. I forgot which one. Maybe I resampled the GRD into 15 meter. Okay, and compare with a SLC to GRD processed image done in Snap. Okay, and there are one very eye-catching phenomenon, which is when you do SLC to GRD conversion in Snap, between the different burst boundaries, you will be able to see the boundary. Okay, so there will be a line where you have an amplitude difference across the line. Okay, and the reason why is because GRD product is not, okay, you need to remember this carefully, it is not a second product from SLC. They're actually both a product from something called level 0 SLC. Okay, so imagine you have some kind of level 0 data sitting inside InSAR. Okay, and one of the processing pipeline generates the SLC. Okay, another processing pipeline actually did some kind of internal interpolation in order to generate the GRD products of 10-meter spatial spacing. Okay, so some people misunderstand the generation of GRD. Okay, it is not a second product of SLC, the level 1 SLC that we retrieved from Alaska. It is a product from the level 0 SLC. Okay. All right, so let's go back to your question. If you are only trying to do GRD, to do amplitude-based change detection, okay, or you can say intensity-based change detection, I would suggest using GRD will be totally enough, and it will be actually much, much faster than using SLC. But if you want to also use the coherence, something we call the interferometric coherence, okay, information in your change detection, then you have no choice. You have to use SLC, okay? So depending on if you want to use coherence or not. Okay, so Louis, I hope I answered your question.
Can you hear me, ma'am?
Yes.
Actually, I have a doubt, like how can we generate layover and shadow mask appropriately?
How can you generate what, sorry?
Layover and shadow masks.
Oh, okay, yes. You mean in Snap, right? We're talking about that right now.
Yes, yes.
Okay.
Is there any another option you can refer to?
Yeah. Let's go back to the demonstration, okay? Because it is right here below. Now, in this window, please select Layover and Shadow Mask. Here you go. It's just that easy, right? You just check this option, then you will get it, okay? And in the meanwhile, sorry?
Actually, I tried with this option, but it is not very nicely done with this particular.
Okay, so if you think it is not very nicely or it doesn't agree with your expectation, then I will highly suggest that you try the other option, which is the one I just mentioned. Sorry, the one radar, geometric terrain correction, and the SAR simulation-based terrain correction. Okay, so this option goes through an additional step, which is to simulate, use the DEM to simulate the radar image. Okay, and then from there it calculates the layover and shadow mask more accurately than the one that we're using. The one that we're using is only using the orbital information. Okay, so it is not as accurate. All right, but as I mentioned, this option, SAR sim terrain correction, takes much longer. So don't do it now. Okay, you can do it later and maybe show us the comparison if you are willing to do a final presentation. Okay. All right, so layover shadow mask, click that. Incidence angle from ellipsoid, also click that because this will give you the information about the incidence angle. Okay. If you are also doing landslide, okay, so for some of you who is doing landslide work, you will need to also please look into this information called the local incidence angle. Okay, I'm not going to go through the details, but this one is highly relevant to whether if you are going to see the landslides or not. Okay, so you can also click that, okay, if you want. All right, so finally, let's write it out, right? Okay, write the output. So it will automatically generate some kind of a file name for you, but I think it's too long. I don't really like it. So I think in the in my work, in my slide, I say just rename it something like a 2018 0905. Okay, and the directory you just put it under SAR course project and Japan. I think that's what I put. Okay. Before you run, okay, don't push your run button now. Just remember to save because later we're going to use this template to speed up our demonstration. Okay, save. Okay, you see I already have a lot of XML files. Okay, I think I previously saved it as, you know, you can just name your whatever you like as long as you remember. Okay, GRD graph crop Hokkaido. Okay, that's what I put in this slide. Okay, you can use the same name as well. Okay, click save. Okay, if I already have it, so just overwrite and then run. Okay, hope you are with me. Okay, it's going to take some time to run. If you have any question, you can just take this chance to ask. Okay, I'm done. I hope you are done as well. Okay, so I'll close this window. Before you close, make sure you have saved, okay, the graph file. Okay, now if you are like me, you see nothing, okay, you go to on the left panel, okay, I'm at this tab called the color manipulation. That's why I don't see anything. You need to go to Product Explorer. All right. And then you will see the product you just generated. Okay. Go to bands. Let me shrink this one. Okay. Then you see all the products, sigma naught, okay, VH and VV bands. Local incidence angle, as I mentioned, this is the information you need for landslide analysis. Okay. Incidence angle from ellipse. This is the view angle of the satellite. Okay. Layover shadow mask. Okay. Now I'll just open that one, the sigma naught, the VB. Okay. Okay, so this is the area. Okay, of the, it's actually a area full of volcanic ash. All right, this is Japan. Remember, okay, has a lot of volcanoes. All right, so we're moving on to session 4, and this one is going to be way much faster, because what we're going to do next is that I open the graph builder again, and I'm going to load the graph and choose the one I just created. Okay, GID graph crop Hokkaido. Okay, open. All right, so you just see the same graph again, and this time in the read tab, I'm going to select my second file. Okay, the file acquired after the earthquake. Okay, so in my case, I have the image on September 17th. Okay, usually I would just click through each one just to make sure that nothing strange happened. Okay, the same. Don't need to do anything. Okay, in the terrain correction, I noticed that the layover and shadow mask. Remember, we actually checked that in the previous slide, right? In the previous when we processed the previous image, but actually after you reopen the graph, this one always unchecked. Okay, so if you like, you can check it again. But in the case of Sentinel, because the orbit tube is pretty tight. When we say orbit tube, we mean when it repeats, when it visits the same place on Earth. Okay, the satellite orbit is within plus minus 150 meters among one another. Okay, that's why we're saying the orbit tube is very tight. So in that case, the viewing geometry is going to be pretty similar between different dates. Okay, so you don't really need to regenerate the layover shadow mask. You probably don't need to even generate the local incidence angle and the incidence angle even. Okay. However, if you are not using Sentinel, okay, in any case, you have a chance to use other satellites, such as TerraSAR X or Cosmos SkyMed, okay, or the ICE-I from Finland. You need to remember that their orbital tube is not that tight. So you do need to look into the layover and shadow mask for each individual image, okay? So now finally, let's write, okay? So I'll call it 2018-0917, 2018-0917, okay? And save to the same place. And as a good habit, before you run, you always save, okay? And I save it as a Hokkaido 2, okay? The reason why you save is really for your own record, what you had done to the image, okay? You want to be able to recall whatever processing you have done in order to check if you did anything wrong, okay? Save, run, yes. Okay, any question? Oh, I see another question from Luis. A value for the baseline where we should check the box for those parameters, or is the unchecking only applicable for Sentinel-1? I would say probably only applicable for Sentinel-1. Okay, if I'm going to process any other satellite images, I will always compute the shadow and the layover and shadow mask. Okay, because in my experiences, for example, ALOS. Okay, I'm talking about ALOS 1. Okay, ALOS 1. Actually, SNAP can read in ALOS 1. Okay, the first generation, and the orbital tube can drift significantly. Okay, plus minus 1,000 meters. Okay, so that will give you significantly different shadow and layover area. Okay, and in the case of TerraSAR X, I also see the baseline drifting, maybe not consecutively. Okay, I mean, when I say consecutively, I mean today and the previous image. Okay, maybe between these two images, the drift is little. Okay, but between many images, the drifts can be a few hundred meters actually. Okay. But of course, you can always make a simple, or you can always just check one or two images. Or if you are careful enough, like what you said, you can check the baseline values first before you determine if you want to calculate the layover and shadow mask. Okay, it's all up to you. Okay, but for Sentinel, I'm pretty certain that it's okay to compute only once. Okay. That's why everybody loves Sentinel. All right, so now we have the second output on the screen, and you see I only have sigma naught, okay, VH and BV, okay, so I'm opening the second one. Okay, thank you, Luis, for nice questions, okay. All right, so my next topic is session 5, about how to properly, because at this moment, okay, you probably want to quickly visualize your results in SNAP. Of course, some of you may be familiar already with exporting the result into a GeoTIFF, right? And opening the GeoTIFF in a GIS software, okay? But still, you can quickly visualize your results here. But you need to know that you need to be fine-tuning the display parameters in order to make sure you are comparing apple to apples. Okay. So the first one, the first thing to do is to go to the view. Okay, I already have this done. You only need to set up this once. Okay. Synchronize image cursors, synchronize image views. Okay. And then now let's go to our first image. Okay. Let me pull this. Okay, now we're in the Product Explorer. Please go to the color manipulation. Okay. So one thing you need to remember is that here, when we are talking about sigma naught, okay, it is actually a linear scale. Okay. It is not in a scale that you are seeing in most of the scientific papers. Okay. In the scientific papers, they actually present the data in log scale, okay, and it's actually dB, okay, decibel, okay. So in order to present your data in the way that you are supposed to see in scientific papers, you need to click on, okay, go to slider, okay, click on log 10, okay. So in log 10, you can easily see. So let me click and unclick. You see, in a linear scale, okay, the value is actually from a value very close to 0 all the way to some, it's actually not even the full range. Yeah, not sure how to do that. Okay, it's quite strange. But anyway, it's actually distributing non-Gaussian distribution, okay? So that's why people like to go to a log 10 scale, because in a dB scale, what you're seeing is more or less a Gaussian distribution of your data histogram, your intensity histogram, or we should say not intensity, the sigma naught, okay? So that's why people use this, because it allows you to use many statistical analysis tool based on the assumption of a Gaussian distribution, okay? So now first log 10, And then maybe for a quick display, let's just click on the trim to a 2 sigma display. All right. So now you're seeing 2 sigma decibel unit, okay, display of your sigma naught. Hope you're with me. Now, once we fix the display of your first image, there's a quick way to apply the display to the second image, which is that you go to the table, okay, and there's this icon, the button here. There's no name, okay, but anyway, you just, oh, here it is, apply to other bands. So click on this icon and click on this one, because it's only going to show the other bands, okay, not itself, the other bands. Okay, so this one means the second product, the sigma naught VV in second product. Click OK. And then be careful when you say, do you want to automatically distribute point of color palettes between min and max? It's actually saying, oh, am I supposed to adjust the display value? Okay, make sure you click no, okay? Otherwise, you're not going to apply the same display scale between the 2 images. Then later when we toggle, you are not going to be comparing apple to apple, okay? So in order to be able to visually compare the 2 images, make sure you click on no. Okay, so now we click the no. Okay, then the next thing is to tell you how to toggle on Snap. Okay. So here, okay, of course you can, manually toggling between the 2 channels, but this is really inconvenient, right? So the thing to do is to go to what you have on the right-hand side, a tab called the Layer Manager. If you don't have the Layer Manager, okay, if it doesn't appear, you can go to View, okay, sorry, the tool windows, okay, Layer Manager, okay, you click it and then it will appear at the right-hand side. So now you choose, for example, I'm actually on Granule 2, okay, it can be either one, okay, so I'm at Granule 2 or the product 2, sigma naught VV, okay, now we have this sigma naught VV here. You click on the plus, the add icon, okay, add layer. So what do we want to add? We want to add image of band, okay, click next. And now remember, we're actually at the second product, right? The 2008, September 19 product. So you want to add the product from the band from the first products, okay, the 2018-0905. And you want to compare the same polarization, okay, sigma naught VV. So you finish. All right. Oh, by the way, sorry. I think I forgot one thing. Okay. So remember in sigma 1 VV, we actually came to the color manipulation, the slider window, and click on log 10, right? And then what we did next is to apply to other band. However, if you go to the second band, you will realize that the log 10 scale is not automatically applied, okay? You need to be very careful. I actually have this part in the PowerPoint, but I forgot to mention. So you need to come here first and click on the log 10 first, okay? And then go back to your, so always remember the log 10 icon is not automatically turned on, okay? You always need to turn on manually, okay? And come back to sigma 1 table, okay? And apply to other bands and apply again, okay? And do not stretch, okay? Do not automatically redistribute the values, okay? Now these two are comparable. Okay, so now come back to the layer manager, okay? Now I select at my first icon, my first product, okay, sigma naught VV, and the second product, of the second date is below me, right? So what you can do now is use your space. You use space. You can turn on and turn off the image. Okay, I hope you are trying on that, and use your mouse wheel to zoom in. For example, let's zoom in to this area. Okay, come to Layer Manager. Okay, and let me turn off. Oh, this is the second date. Okay, turn on is the first date. Okay, second date, first date, second date, first date. So you're seeing a lot of sigma naught differences. Right? Can anybody tell me what are these? Here's the fun part. Let me call somebody to check if people are listening. Just kidding. All right. Anybody volunteer? Otherwise, I'll just call somebody. Okay. Just to make sure you're not falling into sleep. No one volunteer? Okay, let me call Luis. Luis.
Hi, ma'am. Good afternoon.
Hi, good afternoon. Do you have any guess? What are these?
In terms of the ground object, ma'am, I apologize. I don't. But it seems like these are objects that suddenly dropped in terms of the reflectance because of the sudden drop in the sigma naught values.
So do you, based on the shape, okay, of the changed patches, do you have any guess? What could they be?
Maybe these are urban areas. I'm not sure, ma'am.
Okay. So thank you. Anyway, thank you for describing what you observed. Okay. Actually, these are changes. Yeah, vegetation. These are changes of the crop height. Okay. Because remember these 2 dates. These 2 images are what? 12 days apart, right? So of course, one possibility is that, okay, during so the brighter is the first date, the darker is the second date, right? So of course you can say, oh, maybe they already, harvested paddy fields, right? The rice crop, okay? So when you harvest, then the intensity changes because you no longer sense the top of the rice plant, something like that. But anyway, this area, based on the shape of the polygons, okay, is actually quite easy to identify that these are just the crop fields, okay. Although I don't really know what other crops do they grow in Hokkaido. All right, so let's come to the mountain area. Okay, so that's the key area, right? So now we're in the so let's toggle. You can also try. Okay, so we're in the first image and the second image. Okay, first, second. Okay, we can zoom in a little bit. Okay. The first, okay, second. Oops. Sorry. First, second, first, second. Okay, so can anybody tell me, do you think, okay, so what I'm saying is that, okay, so assuming that I know the true answer, okay, because I studied this area. So I'm telling you, you're actually seeing a lot of landslides right here, okay. So can anybody tell me, do you think you're supposed to see intensity increase or intensity decrease in a landslide area? Anybody want to guess?
It should be increased.
It should be increased, and the reason is?
I think it should be like roughness increased in the surface.
Okay, so it changed from vegetated area to a bare surface, correct? Is that what you mean?
No. I think like some due to some collision or something, like a slide into some structure, ground structure may be changed. And
okay. Sorry, I'm actually answering some question for you. So okay, so actually, okay, Well, still thank you for your guess, okay? Because in many cases, we like to assume that when a landslide occurs, okay, the trees slide down, right, and a bare surface is exposed, right? Surface becomes smoother, right? Louis also mentioned, okay. So you're supposed to see a higher reflectance, okay. That's the general expectation of a landslide. Okay? So, however, when you toggle between these two, okay, so again, this is before, this is after, okay. You need to agree that even though this landslide is very well studied, okay, in the SAR change detection community, you have to agree that you don't really see much of the intensity increase in this case, okay, at least based on toggling these two events. Okay, you sometimes can even feel, oh, maybe the pre-event image, okay, the image acquired before the landslide looks brighter than the post-event. So this is post, this is pre, right? The pre-event looks brighter. Okay, so to be honest, this is a landslide study or landslide detection using SAR is more complicated than a simple assumption of changing of the land cover type from vegetation to bare soil. Okay, it's more complicated than you and I can imagine naively. Okay, so that's why landslide detection using SAR is still a very active research area. Okay, people are trying to understand what could be the complicated factors that affecting the detection accuracy of landslide by using SAR. Okay, so I choose this example is because first, it is one of the best known example of landslide change detection using SAR. Second, it demonstrates how complicated this case is. Okay, if you want to challenge yourself, you can try this topic in your final project, but it can be a bit difficult. Okay, so if you want an easier one, you can actually try the flood detection, which I will be talking about in another 2 weeks. Okay. All right. So it's pretty much about the backscattering coefficient. Okay, sigma naught. Okay. Oh, there's a last one, image alignment. Okay. So why do we talk about this? Okay. So it's actually a small technical detail, but if you ignore this detail, people may think you have some kind of problem in your research. Okay, so let's zoom in to a very local scale. Okay, a pixel scale of your image. All right, so we're in a pixel scale, right? Okay, so try to toggle between these two. So I'm toggling on the screen, before, after, before, after, before, after. It may be difficult to see from my demonstration, but if you toggle on your own window, you will see that the pixel boundaries are not aligned. Okay, and it is mainly because we're using for example 1 second, okay, SRTM DEM, but we're giving an AOI that's not really cut right on the 1 second boundary of the SRTM DEM. And when it is doing the terrain correction, aka geocoding, okay, equivalent to geocoding, then it's trying to geocode based on the AOI that you appointed, not based on the exact boundary of the SRTM 1 second grid. So that's why you always will see a misalignment between the images, okay? And also, it's also because your images are acquired at different path, okay? With a different range and pixel location on the ground, okay? So in order to do a proper comparison, you always need to make sure, finally, you are registering all your images to the same grid, okay? Usually we choose one image as the reference, and we register all the other images, depending on how many images you like to use to do this analysis. Okay, we always register them to the same reference image. So for example, right now, I may like to use the one before, okay, which is my first product, as the reference. Okay, so then what I'm going to do now is to go to, so then because this is the reference, so I just leave it here and come to my second product. Okay, the second product need to be realigned. So you go to raster. Okay, geometric. Okay, and sorry, geometric reprojection. Okay, so now the source, the one that we want to reproject is the after, the post-event image. Okay, and you can call it aligned. Okay, which means that we align the image to the reference image. Okay, save to the same product folder. And in the reprojection parameters, make sure you use the CRS of your first product. Okay, so that the grid boundary will be forced to be the same. Okay, so this is the critical point. Use the CRS of this and run. You want, yeah, already have one called this name, but anyway. Okay, now it's done. So let's open the one aligned, okay, VV. Again, as I mentioned, the log 10 scale is now automatically turned on. So you turn it on first and come to your reference image, go to the table and impose the color scale to the new aligned image, okay. Check the third image and do not stretch. Okay. Okay, so now let's toggle again. So now I come to the third aligned image, okay, and we do it again. We add the layer of the reference image. Okay, choose the image of band and choose the pre-event image, product 1, VV band. And finish. Just check this. Okay, so you can zoom in and toggle just to make sure that they are aligned. Okay, now they are perfectly aligned. And this should be the base of your analysis. Okay, so never forget to do this. All right, any question? If not, then this is the first part of today's demonstration. And then, let me see, I will send you the okay, so think about any question if you have any. And then I'm going to send you a package of the graph files for our second part of the interferometry. Okay, let me see, where is it? Sorry. Okay, here it is, the link. I'll put the link in the chat box. Okay, so please download this package now, unzip, and place the XMLs under the XML folder. All right. So when you unzip, you are supposed to see 01 to 07. Okay. Give you like 1 minute. Any question, you can just speak out. Yeah. 01 to 07. Okay. There should be this 7 in the package. And please place them under the XML folder. Okay, I assume most of you are done. Okay, and then I'll come here and clean up all my results from the first parts. Close all products. Now. Okay. Now let's come to session 7, and so just a quick information. This demonstration is for an earthquake that happened in Taiwan. Okay, and we're going to go through the demonstration, and in the meanwhile, I'll talk about a few technical details regarding processing and interpreting interferograms, because there could be a bit more technical details, so I may not be able to finish what we talk about the slides, the following slides today. So if I cannot finish, don't panic. I will continue on from my next session, which is 2 weeks from now. Okay. So, or feel free to continue on by yourself, and then try to think about, because I actually put some questions inside the slides. Okay. But anyway, so the event is a magnitude 6.6 earthquake that took place in Taiwan back in the year of 2016. Okay, and because I chose this one is because the area is quite small, and also the signal is quite clear. Okay, and in order to save your computer from overloading. All right. Okay, so again, let's come to the graph builder. Also, sorry. The first one is that let's try, because I already give you the graph files, right? So let's also try the batch graph, the batch processing by using graph. Okay, so open this window, click on this icon. Okay, not this one. This is for batch processing, and let's load the graph by clicking on the 01 SLC graph load. Okay. All right. So here are the 4 tabs representing the 4 blocks that you previously see in the graph builder. All right. So now let's first, in the I/O parameters, click on add, and now it's no longer Japan. Let's go to Taiwan. Okay. So you can shift and choose 2 images at the same time. Okay. So it's going to get the information automatically by itself. Then go to top split. Okay, so the cool thing here is that it actually directly visualizes the bursts. Okay, so you may wonder, you keep talking about burst. So what exactly is burst? Okay, so just think about a burst as a single. Again, I'm using the middle wheel to zoom in, and the right button to move. Okay, so think about burst as individual small SAR images. Okay, so actually each sentinel frame is composed of 3 different swaths called the swaths 1, 2, 3. Okay, and swath 1 is always the one closer to your satellite. Okay, and judging from the orientation of this image, we can tell that this image is acquired through what we call ascending track, which means the satellite is flying northward and slightly westward. Okay, and because Sentinel-1, and as well as most satellites, but not necessarily all satellites, okay, SAR satellites, are mostly looking to the right. Okay, so we know the satellite is moving to the north and looking at the right. Okay, so the one closest to the satellite, something we call the source 1, followed by source 2 and source 3. Okay, so according to the slide, I already tell you we need to choose on source 1, and we usually use VV mode. Okay, and then we like to use the 8th burst. Okay, the way to choose the burst is by dragging this small triangle at the left and the right. Okay, so you just move, and then you see the number here changes, right? So we want to from 8 to 8, 8 and 8. Okay, 8 to 8. Okay, so now you know it's right here. Okay, the image is located right here. Next, go to apply orbit file. Okay, again, you just do sentinel precise and check this do not fail. Okay. Finally, in the right, let me see what I put. Okay. Oh, I say do not change the name. Okay. The reason is because if you change the name here, I don't really know if these two will be using the same name. Okay. But it actually, by using the default name, is automatic. The output from these two inputs will be automatically saved to 2 different files. Okay. So don't change the name. And here you save it to project and Taiwan. All right. Okay, once you're done, just click Run. Okay, so I'm done on my side. Okay, so if you like, you can click on the bands and see what are the bands. And these are exactly what Dr. Alan Tsai has mentioned, right? There's an I band, there's a Q band. All right, okay, so this is the quiz time. Let me ask. Let me just check if you listen to the talk carefully. Okay, not sure who I should call. Let me see. Okay, so maybe Edgar. Sorry, I'm calling people who ask me questions. Hope you don't mind. Okay, so Edgar, are you there? Uh-oh. Cannot hear you. Okay, so let me call someone else. I saw there's a name, very cute name called Micah or Mika. Hi, are you there? Okay. All right, let me try last one. Otherwise, I'll just answer by myself. Okay. Okay. Let me call the Sun Pingming. Hello, are you there?
Yes.
Hi. Yes, sorry, you got caught by me. So,
yes. Good morning. Good afternoon.
Good afternoon. Do you remember what does I and Q mean based on Dr. Alan Tsai's talk?
Not sure.
Okay, that's fine. All right. So I call you just to, wake everybody up. Okay. Maybe people already fell into sleep. Okay. So I and Q represents the real and yes, Edgar, thank you. Imaginary.
Yes.
Right? Because we know radar wave is complex number represented by a real and imaginary part. All right, so here you are going to see the I band and the Q band and a V, which stands for a virtual band. So that means it will appear only when you click on it, okay? And it's being calculated on the fly. Okay, when we say on the fly, it means it's being calculated in the real time by using the information from I and Q band. Okay, so anyway, you see there's IQ from the first date and the IQ from the second date. Okay, now let's move on. Okay, the second bar, let's form the row interferogram. So go to the graph builder. Okay. And the load 0, 2. Okay, so let's directly load the 0, 2. And let's observe what's included in this flow. Okay, so basically the idea is that you read in the pre-image and the post-image, right? And you do back geocoding. So the back geocoding is something more like okay, taking the SRTM information, okay, into the radar coordinates, okay, or take the so-called geo longitude latitude coordinates back into the radar coordinates, okay, by using the satellite orbit information, okay, because later on we need to remove something called the topographic phase, okay, so we need to have this done. And I think it's not clear in this in this workflow, but I believe at some point you also need to align the two images, okay. It's not clear here, but it's probably part of what's inside here. Otherwise, it doesn't need two inputs, okay? So again, just like what we just did now, in order to form an interferogram properly, you also need to align the second image to the reference image. Okay. And then followed by a step called enhance the spectral diversity. So what does that mean? Okay, the acronym is called ESD, okay? So remember, just now, when we try to select the burst, there are actually many, many bursts in a single swath, right? Okay, and I just said that each burst is considered an independent SAR image. So the problem is that so this is very specific to the Sentinel-1 or Sentinel-1A or 1B, okay? It's very specific to this node that between the bursts, okay, usually you will see an offset, okay, between the bursts. So this ESD is actually designed to estimate what's the offset. When I say offset here, I mean the phase offset, okay? What's the phase offset between the two bursts in order to be able to merge the interferograms from each bursts together to form a large interferogram. Okay. So, because today we don't have multiple bursts, we only process one burst. So what you need to do now is you need to click on this block and right-click and choose delete. Okay, so that it's going to skip the ESD. But just remember, if you have more than one burst, you always need to, or it's recommended to include the ESD. The job won't fail if you don't include ESD, but chances are you are going to see a horizontal line in your interferogram representing the burst boundary. Okay, now let's link. So once it's done the geo to radar back geocoding, just do the interferogram and write. Okay. All right, so let's save this modified flow first. Save to, I call it 02 SLC graph row FG underline no ESD. Okay, just to remind myself that I didn't do ESD in this case. Okay. And as I mentioned, ESD is not mandatory. If you have multiple bursts, you can always choose to skip ESD because ESD usually takes a long time. Okay. All right, so back to the products, back to the first tab. In the read, according to my slide, okay, let's choose the post event, okay? So the one that took place on February 14th. Okay, in the read tab. Now in the read to tab, choose the pre-event. Okay, so the one on February 2nd. Okay. The first one is February 14th. The read to is February 2nd. Okay. In the back geocoding, you don't need to do anything actually, just keep the default. In the interferogram, you don't need to do anything either. Oh, you actually can check. Remove this one, subtract topographic phase. I think that's what I suggested here, okay? see, yeah, uncheck the subject topographic phase, because later on we can do that separately, okay, in a different block. Okay. And finally, right, okay, and I think my suggestion just for easy recognition is called the row IFG. Okay. And then the location, again, is supposed to be in Project Taiwan. Okay, and if you like, you can save again. Okay, it's always a good practice to save it before you run. Okay, now let's run. So no questions so far, I guess. So you see, it's very easy if somebody handed you their workflow templates, right? Then by using these workflow templates, it's very easy to to complete some particular type of data processing. And there's one more thing that I didn't mention about Snap is that actually it has a very big user community, and on the user forum, Snap user forum, that actually people share a lot of this kind of graph. Okay. They may not necessarily show the XML file directly, but they usually print out the screenshots of the block, okay, the workflow. So that's why if you want to try something new and you're not pretty sure, you can always go to the Snap forum and Google based on keywords. Include because we're going to do it later, okay? Well, you can always do that here and ignore the topographic phase removal in the next step. Okay, either one, actually. All right, so now it's done. Let's close this window. Open the row IFG. Okay, now you see it passed over the real band, the imaginary band, and the two virtual. Okay, you see it's actually virtual files. Okay, and this is the phase. Let's see. Okay, so it looks like that. It's pretty noisy. Okay, not beautiful. Okay, and there's another band called coherence. Okay, so coherence, so you can see the values are, let's see, basic. So you can come to the color, the basic mode, and change the value from 0 to 1. Okay, that's basically what is the full range of the coherence. And in the scheme, you can change, choose a random one. Okay, and sorry, the color changed. All right, so this gives you a clearer view of what it looks like. And actually, only part of image give you a really nice coherence. Okay, so again, coherence indicates some kind of quality of your interferometry. Okay, if your coherence is low, when we say low, how low is low? Maybe I would say 0.2, 0.3 is really low. Okay, so actually a lot of this area has pretty low coherence. Okay, but still later you're going to see that we can still generate produce a better interferometry than this row one by applying a filter. Okay, so now let's move on. Okay, filter the interferogram. Let's load graph. Go to 03 graph field IFG. Open. Okay, so it has quite some steps. Let me broaden the window. Okay. So it's quite funny that once you're reading, so automatically it captures the row IFG in this place. Okay, And it's quite funny that it requires this top SAR. Top SAR is actually the acquisition mode of Sentinel-1, okay? And it asks for deburst, okay? When we say deburst, it's something similar to saying burst mosaicing, okay? Which is to mosaic a different bursts together. And I actually try to remove the block, okay, from this flow because it doesn't make any sense that you need to deburst when there is only one burst, okay? But it turns out that the work actually failed if you remove it from the flow, okay? So anyway, we just leave it there. Okay, so back to Louis, right? Is that Louis' question? Yeah, back to Louis' question. Yes, you either can do it previously or like this one, okay? So I'll check that one because I actually have a block here, all right? So for the topo phase removal, okay, you can just keep the default parameters, okay? And make sure that this is the 1 second HGP, okay? So next, multi-looking. Okay. So the term multi-look is actually a very SAR specific term, okay? Because if you go and ask other people who do optical image processing, and you tell them, oh, we do multi-looking, and people will be looking at you saying, what are you talking about, okay? What does it mean by multi-looking? Okay, so multi-looking is somewhat similar to downsampling, okay? So, so there are, you know, like all these jargons, such as like an up look and down look, okay? So it sounds pretty funny, but up look means you are making the sampling denser and denser, okay? It's called the up look. And if you say down look, you mean you're making the spatial sampling coarser, okay? And by how much times? By the number of looks. That's exactly here, okay? So you see the default parameter, which is the parameter constantly adopted by Sentinel-1 InSAR processing, is they like to take 8 looks, which means 8 times coarser in the compared to the original SLC resolution in the range direction. And you may wonder, oh, wait a minute, you just said the term range and azimuth, okay? So I think Alan also mentioned that, but some of you may already forgot. In order to speed up, I just mentioned. So range, you can consider range as the X in the radar coordinate, okay? And the azimuth is the Y in the radar coordinate. And then you ask, what do you mean by radar coordinates? Here it is. This image is in radar coordinate, okay? Which means that in this coordinate, satellite is flying directly along the y-axis, okay? Although in the real world, the satellite is flying slightly toward the northwest, right? So that's why immediately we know this is a radar coordinates. And of course, because we haven't done any terrain correction or so-called geocoding, right? So we know it has to be still in radar coordinate. Okay, so this is the range direction or the x-axis. This is the azimuth direction, which is the y-axis. Okay, so we do h/2, and the reason that we do this is because we want to keep the georeference square pixel. Okay, we want the pixel to be relatively square, and why it has to be 8? Then you can immediately understand, because originally the SLC or the original radar SAR image, the range, so-called resolution, okay, let's just call it resolution, has a smaller number. It's actually about 4.5 meter in the range direction. And in the azimuth or in the y direction, the corresponding spatial or ground resolution is somewhere around 14 to 15. Did I just say kilometer? Sorry, meter. Sorry, 15 to 14 meter, okay, in the y-axis, in the y direction, and 4 to 5 meter in the x direction. Okay, so that's why if eventually you want to form a square pixel, you need to properly calculate what should be the right number in range and in azimuth. Okay, and of course for Sentinel, because everybody is so familiar with Sentinel. Okay, so it's probably, you know, it's not a big deal that, or it's quite straightforward. Oh, it's 8x2 or 7x2. Some people do 7x2. But then when it comes to all the other satellites, it's very crucial that you understand what was the original resolution in the SLC image, what's the range resolution, and what's the azimuth resolution, in order to determine the best number of looks to take. Okay? All right. And the most important thing, we apply a Kuo-Hsin phase filter. Okay? So this is the filter that will, okay, of course we're not going to talk about the filter details, but basically it will suppress the noise, okay, and enhance the coherent part of your fringe patterns, okay? And the key, actually, if you are also thinking of a mini project, this part, as well as the multi-looking part, will be the key parameters you should try, okay? Because sometimes, I don't know if you ever have this experience by looking at other people's interferogram, okay? For example, if people are, you know, working on an earthquake or whatever, you know, surface processes, and you just feel, how come they can produce such a nice interferogram and mine is so ugly, okay? And a lot of time, you need to work on the multi-looking and the filtering parameters. Okay, let me see. We have the question. When doing multi-looking, should both the range looks be at least 2? No, it's not necessary. Okay, it can be an odd number, because remember it's looking down, right? So when you look down, you just odd number, just like a collecting 7 pixels into one. Okay, but I believe if you are trying to do up looking, okay, then you probably need to go even numbers. Yeah, otherwise it's difficult to cut the pixel into, for example, 3 pieces, I guess, where I don't really know. But my recollection is that usually it's even number if you do up looking. Okay. All right. So please take my words. All right. Multi-looking, the number of looks, and the Kuo-Hsin the Kuo-Hsin phase filter are the key parameters that affects the quality of your interferogram. Okay, so let's just keep these default parameters for now. And finally, let's write. So let me see what name I put. I think I put like a field IFG, something like that. Yeah, field IFG. And here, make sure that you have the name, the folder location correct. Okay, Project Taiwan. All right, so if you like, you can save it again. Save, okay, override your existing one. Okay, 03 graph field IFG. And run. Yes. Okay, so now we're done with the filtering, and let's open the band. Okay, I think just now I opened, yeah, the face, the virtual band. So let's open the face. All right, so now it looks quite different from what you had. Okay, previously it looks pretty stretched in the X direction, but then because remember we are taking different number of looks in the X and Y direction, right? In the X direction, we are combining every 8 pixels into one, and that gives you this, right? and in the y direction, we're combining every 2 into 1, okay? So that this, this extent actually closer to the actual geospatial shape, although it is still not oriented in the right way, because we know this is still in the radar coordinates, okay? It's not being geocoded into the actual geo coordinates. Okay, now let's move on to the slightly difficult part, okay? That will require you to go to your Linux and Windows, okay? So first, again, the graph builder, let's load the graph, which is the UNW export. So you may wonder, what does the name mean? Okay, why a UNW export? Okay. Oh, by the way, so before going to something called unwrapping, okay, maybe I should ask some of you, why do we need to unwrap? Okay, what does it mean by unwrap? Okay, so using these values, okay, using this graph. Okay, I don't know if there's any volunteer. Okay. Okay, so there's one more question from Luis. Will there be a significant difference if we use SRTM 3 and 1 for topo face removal? To be honest, I don't know. I haven't tested, and I guess it really depends on how much error in the SRTM 3 and 1 in the particular place that you're studying. Okay, so if in the studying in your AOI, the SRTM 3 and 1 are significantly different, then you probably will expect some more difference. Okay. All right. So, Dana, you ask questions. I hope I didn't discourage people from asking questions, but I do encourage you to ask questions, and then we can have more interaction. So, Dana, are you willing to try to answer this question? Like, why do we bother to do face unwrapping?
Hello.
Hi, Dana.
So, I think you do face unwrapping because when you only have the face, you don't know exactly what the elevation is, because your face is a number that repeats. So you unwrap to retrieve the original elevation data.
Yes, thank you. Yes, that's correct. Okay, so to help some of you, some of the newbies, okay, we can quickly check what does Dana just mean. Okay, so if you can go to the upper left, one of the tab called the pixel info. Okay, in the pixel info, you just move like randomly on this filtered interferometer. Okay, and that, for example, let's start from this like a cyan color. Okay, so it's about -3, right? And you gradually move inward. Okay, you start to see that it goes from -3 all the way crossing 0 and to +3, and suddenly it jumps back to -3, okay, at about the same color. All right, so this is because the original phase information only detects the changes between -pi and +pi. Or here, yeah, so it's -pi here and +pi here, and it dropped back to -pi again, forming another cycle. All right. So this then cannot tell you the exact meaning of this interferogram. And then Dana just mentioned that this is elevation. Actually, what we're seeing here is no longer elevation, because when we are doing the filtering, okay, so let me quickly open the flow, 03, okay, we actually have this topo phase removal. That means we already estimate what should be the phase caused by topography and remove that, okay? So therefore, what we are seeing right now is no longer, or we should say not mainly contributed by topography, but actually contributed by deformation caused by an earthquake. Okay, so you're saying, oh, the earthquake is causing this kind of a concentric pattern. Okay. Okay, so now let's move on to the unwrapping. So the reason why 04 step is called a UNW export, it actually means you need to export your data to the unwrapper. And the unwrapper is called a snafu, which I believe you have already followed the instruction to complete the installation of snafu in the virtual Linux on Windows. Okay, so now let's export out the filtered interferogram, okay, in the read tab, and go to the snafu export. Now here you need to specify where to store your snafu folder. Okay, so again, as instructed, it should be under some of your project folder, okay, the SAR mini course project folder, Taiwan, and the snafu. Okay, there are actually different modes of snafu. You are welcome to give it a try. Okay, but anyway, we just keep the default parameter. Okay, number of tiles, a number of rows and columns, just keep it to 1. Okay. All right. So again, you can choose to save it, export, and run. All right, so it should finish very quickly. Now next, let's go to our Linux on Windows. Okay, so now, let's see if my text is too small. Oops. Couldn't seem to make it bigger. Let me see. Properties. Okay. All right. Much better. Okay. So so usually when you enter, you will be feel like I'm teaching Linux. You'll be under some kind of home and your local username, okay? So as instructed in the PPT, you need to go to a location called the mount, okay? That is the location where your Windows data files can be communicated with your Linux data files, okay? So your C drive will be mapped right under the mount, okay? So now you enter the C folder, then you are supposed to see all the files under your C folder. Okay. So now I'm going to directly navigate to the location where I store the TSU folder. Okay, so I'm under the SAR mini course now. Okay, and I need to enter the project, okay, the place, and under Taiwan. Okay, so now I'm under the project Taiwan, and remember we actually saved the output to snafu. Okay, the snafu export, the final output is stored to the folder called snafu. Okay, so let's see. Oh, there's in this field IFG, okay, which is the output from the previous workflow. Now we need to execute snafu. So what command to execute? Okay, it's very easy to check. Okay, sorry, these are all Linux commands. Okay, if you are very unfamiliar with Linux, there's really no way, because I have no clue why Snap cannot just include the snafu into Snap. Okay, but anyway, you just do head, okay, snafu.conf, which means to print out the first few lines in this file. Okay, so here it is. Then this line, snafu -f, blah, 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 is the command that you need to directly type in your command line. Okay, so maybe we can just select this one. Okay, and then you for example, you select it, and then hit enter. It's actually being copied. And then you just right click it will be it will be pasted. Okay, sorry, it's just again some Linux things. All right, so I hope you can follow. If you don't know how to do that, you can just type it again. All right. Okay, and you just run. Okay, so just a few words about the SNAFU unwrapper. Okay, so in the old times, there when there's no SNAFU unwrapper, okay, the traditional unwrapping method is to identify the branch cuts. Anyway, you can consider that as discontinuities in your interferogram. Okay, and it's trying to get around the discontinuities by minimizing actually they use something very interesting, is like a positive and negative charges, okay, like electric charges. Okay, they identify the positive and negative charges around the discontinuities and try to get through these discontinuities by minimizing the total sum of all these charges around the discontinuity. Okay, but actually in the old time, when we are unwrapping using this way, a lot of time the discontinuity never go away. Okay, and leaving a lot of minor cuts here and minor cuts there in your interferogram, and your interferogram just look ugly. Okay, but then this smart guy, Curtis Chen, who is a guy in JPL now, he invented this SNAFU, okay, with his supervisor, Howard Zapker in Stanford, okay, and this is like a statistically based unwrapping method, okay. So it has you can just think about it as a magical method to minimize the number of branch cuts, okay. So eventually people just feel, oh, a lot of times SNAFU can really, eliminate a lot of the unwrapping discontinuities, or what we say unwrapping errors. Okay, so that's why right now many SAR processing software like to use SNAFU as the default unwrapper for the interference. But of course, SNAFU has a disadvantage. Okay, the disadvantage is if your data is huge, SNAFU is going to take a long time. Okay, so of course then there are a lot of ways to get around this, and so that's one thing. Okay, your data is huge, or you have a lot of noises that creates a lot of discontinuities in your data, then your unwrapping will take a long time. Okay, so of course, there are a few ways to get around this problem, which we're not going to talk about today, but you just need to know SNAFU is not the oldest unwrapping method, and now it almost become the standard, like everybody is using right now. Okay, we're done. I hope you're also done, okay, because we're running out of time. So finally, let's just port the data in, okay, and have a look at the unwrapped result, okay, and then we call for today, okay. Load the graph. Okay, we need to do so. Just now we export the data to unwrapping to SNAFU. Now we import the results back into SNAP. Okay, so choose 05 UNW import. Okay, so in the first one, in the phase read, okay, the first tab, you just choose the one that you select for the export stage, okay, the field IFG. Then in the second tab, you need to navigate to the folder where you execute SNAFU. Okay, so Taiwan, so I run my SNAFU here, okay, right here, okay, and the file you need to choose is the UNW phase, okay, unwrapped phase. And actually these two, HDR and IMG, they belong to the same file. Okay, it's an NV format. Okay, IMG is the actual data block. HDR is the header. Okay, here you need to choose the header. Okay, remember. So select the header file from the UNW face. Okay, and SnapView import is default. And right. Okay, I think my default name is UNW IFG. Okay, and save it to Project Taiwan. Okay, hit run. Okay, so now let's open the UNW face. Okay, here you go. All right. So just now you had all these different fringes as being, concatenated across this Chung-Pai face boundaries into a continuous face field. And of course, you can see still some discontinuities here and here. And yeah, the most eye-catching ones are here and there. Okay. Of course, this one, because we studied this event already, so we know which are the true signals, which are not. But imagine that you are studying an event that you don't have any understanding, and you are seeing discontinuities in your interferogram. The first question you need to ask yourself is always, is my unwrapping parameters appropriate? Are these discontinuities real, or are they still unwrapping errors? Okay. If these are still unwrapping errors, then you need to deal with them in order if you really need the data from this area. Okay? All right, so we will stop here, and then for the slides, I think we are stopping at, let me see, session 10, okay? We are done all the way to session 10. And 2 weeks, my next session, 2 weeks from now, I will continue from session 11. Okay, that's all for today. I'll give it back to Chang.
Okay, thank you, Nina. And in case that you have the double screen, it's not difficult to follow the lecture today. One screen for Google Meet, another screen for Snap. In case that you have only one single screen, somehow it's inconvenient. But Nina, I prepared very good slides. You can follow the step in slides. Okay, it's today's class. I saw a question from Luis. So we finished the lecture today, and Nina maybe can take the questions from Luis.
Okay, thank you, Luis. I saw that you said there's a documentation for SnapView or Snap plugin. I actually don't know, okay? Especially because, to be honest, for most people who are doing really interferometry analysis, time series or like a individual event analysis, we seldom use Snap, okay? We usually use, for me, I use ICE, okay? And many people in Taiwan are using GMT SAR, okay? And if you have some money, I know some people are using Gamma, which is commercial software. Okay, so if you really want to stick to Snap, I think you can still do it. But you probably will need to do some work to figure out whether if SnapView is functioning, can be functioning through an independent plugin. Okay, but still, as I mentioned, if you are still always using a Windows system, if you have a Windows workstation, okay, equipped with a multiple cores, okay, 32 cores, okay, 48 cores, then you're probably fine. Then you can always continue staying with the Snap. But if you knows how to use Linux, okay, then using other softwares will probably be more efficient. Although the learning curve will be much longer than Snap, because today you can tell Snap allows you a very visualized way to study the flow, okay, and also the key parameters for each individual processing step. I think this is the biggest advantage. So you should take it as a learning tool. But if you really need to do work, especially interferometry, I still recommend in the long run you should try to get in touch with those Linux-based softwares. Okay.
Okay, thank you, Nina. That's today's lecture. So see you next week.
I thought there's a question, right? Means Mengze.
Mengze.
Still have Chris to do.
Yes, they had a show quiz.